Three, two, one. Chapter 4. Let's go. Alright, so we are now escaping the exciting world of first order differential equations, and we're now getting larger. Okay, so that's our setting. Higher order DEs, and specifically, we are going to focus in on a very specific case. We're going to primarily look at second order differential equations. A lot of the stuff we're going to talk about can be naturally extended to third, fourth, so on and so forth. I'll interject here or there, but when it comes to what I'm going to expect you to be able to handle, I'll stick to second order things. And for the most part, physically speaking, most differential equations, when we're talking about physical phenomena, 2 is pretty much all we need in terms of the number of derivatives, right? If we think about our unknown function as being position or displacement, right, then its first derivative is velocity, its second derivative is acceleration, and beyond acceleration, we don't really use anything else outside of that. Although there are some notable exceptions. As I've mentioned, a fourth order derivative shows up when you're looking at cantilever beams, and a fifth order derivative was used for the Hubble telescope. So, not that they're not out there, but for our purposes, once you figure out how second order work, then third, fourth, and so on, it's just the same story. Now, the other thing I want to note is that we are not going to consider non-linear higher order DEs. The theory for non-linear higher order DEs is well beyond the scope of this course, so we're going to stick to second order and linear just to make life nice and easy. Okay, so specifically then, any second order linear DE is going to look like this. So we see two derivatives appearing. My unknown function and its derivative may also appear. And since we are assuming linear, that means the only things affecting the dependent variable, the unknown function, are scaling, adding, and derivatives with respect to the independent variable. And in this case, I'm using x as my independent variable. So we have some coefficient functions, and then what can be thought of as like the constant function. So note that this looks very similar to a polynomial. Maybe that's going to show up in a couple of lectures here. Okay, so we want to know how to solve these things. So the first thing to do is to ask, well, can we even solve them, right? Before we hunt a dragon, let's make sure it exists. Good news, it does. And even better news, there's only one. So for initial value problems, second order linear DEs will always have a unique solution. So that's great news. So there's exactly one dragon. You can handle that. So there's the little spot in the scales where you can shoot the harpoon or whatever. But okay, now that we know that there's only one, what are they going to look like? Okay, so that's going to be our main goal for today, is to really pick apart and talk about what are solutions to such differential equations going to look like. And as we're going to see, it's going to be significantly different than the first order case, right? The jump from first order to second order, all of a sudden, there's something interesting happens, and you may already start having it going on in your brain what's going to occur, right? I've already talked about velocity and acceleration. The IVP needs two pieces of information, so right. Okay, so it turns out that for second order linear DEs, we can split them kind of into two cases. And the two cases are, well, what's going on with the right-hand side. If the right-hand side is 0, these are known as homogeneous second order linear DEs. Okay, now we talked about homogeneous first order DEs, and note that that looks different, right? Or is it? Ooh, I don't know. Maybe we'll have a discussion about that. All right. So let's get a feel for such things with a pretty basic example. So here we go. Second order linear homogeneous differential equation. Linear differential equation. Okay, so in this case here, my A2 is 1, my A1 is 0, and my A0 is -1. Okay, now, if I stare at this, right, and again, we always want to just read the differential equation and think about what it's asking. I want a function whose second derivative minus itself is equal to 0. In other words, can you think of a function whose second derivative is itself? Well, the first one that should jump into your head, of course, is e to the x, right? And this is going to be a running theme, especially going forward, that e to the x is our fallback for a lot of methods for solving differential equations, right? And that shouldn't be too surprising. It is the only function who is its own derivative, so that is a very useful property when we're studying equations that have derivatives in them. Now, that's one solution, e to the x. Is there another one you can think of? How about e to the negative x, right? Its first derivative is not itself, because when you take a derivative, a minus 1 will jump out from the chain rule, but another derivative will undo that minus 1. So we have two solutions, e to the x and e to the negative x. Are there any more? Can we find any more solutions? Well, we're focusing on linear DEs, and there's a good reason for that. The derivative is a linear operation, meaning that the derivative of a sum is the sum of the derivatives, and the derivative of a scaled function is the scaled derivative. So if these are solutions, then scaling them and adding them together will indeed create a new solution. Okay. Now, if you did have any experience with these, and I asked, what's a function whose second derivative is itself? You, depending on your background, you may have jumped out with, oh, hyperbolic sine and cosine, sinh and cosh. Yeah, that's right. If you have no idea what sinh and cosh are, or what the hyperbolic trig functions are, don't worry. They sort of show up every now and again. So here is hyperbolic sine. It's defined as e to the x minus e to the negative x, all divided by 2. Hyperbolic cosine is the same thing, but instead of a minus, it's a plus. One way to think about them is cosh is the even part of e to the x, and sinh is the odd part of e to the x. Every function can be broken up into its even and odd parts. I'll leave it at that. If you're interested, go look that up. So sinh and cosh make guest appearances every so often. This might be the first time you've ever ran afoul of them or seen them. Don't sweat these too much. They're just an occasional, like, hey, by the way, this function is equal to this, and there's like a whole bunch of theory devoted to this stuff. So if you're interested, go check it out. It's interesting things. I am old enough, I guess, that when I took calculus, hyperbolic trig was like a whole like section that we covered. We spent like a couple of days on it. Like my Calc 1 final, I remember there was some like ridiculous problem with like solving a hyperbolic trig equation. I was like, oh, I don't remember if I solved it. So, but anyway, I think I was at the cusp where they like were still teaching it in calculus, but then not so much anymore. But anyway. So we can create a new solution. Let's get back to differential equations. There's your tangent for today. We can create a new solution by scaling and adding them together. Right, you can verify. If you take the second derivative of this thing, it's indeed itself. So that's actually one thing about the hyperbolic trig functions. They basically behave like sine and cosine, where their derivatives will cycle through themselves, but no minus signs jump in. So the derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine, so it's a little bit nicer where you don't have to cycle through so many things to get back to where you started. You just got to do it twice. But anyway, so hey, I had two solutions, and by scaling and adding them together, I created another new solution of my differential equation. All right, so let's give this a name. This is called the superposition principle. So if you have two solutions to your second order linear homogeneous differential equation, scaling and adding them together will still remain solutions, right? And the reason this is true is the derivative is a linear operation, and the right-hand side is equal to 0. So they are solutions, so when you take the derivative, scale them up by the functions a2, a1, and a0, and add them together, you'll still get 0. Now, if the right-hand side was something other than 0, this is not necessarily true, but more on that later. All right, so there we go. I love the name superposition principle. That sounds like you're really doing something crazy, right? You're just scaling and adding functions. That's it. But superposition, ooh, that sounds like some high level physics garbage right there. But anyway, okay. So that then naturally leads us to the question: a second order differential equations, two derivatives, two constants should show up in the solution, right? We're going to undo two derivatives. We think about it physically. We've got velocity information, we've got acceleration information, and position. So, right, I should just need to know my position on my velocity, and that should be enough to solve. So this seems to be indicating that all I need to do to find a general solution is just find two solutions and apply superposition, right? You get two answers, scale them up and add them, boom. You have two unknown constants. That should be the answer. Right? How could possibly go wrong? Okay. Hopefully it jumped out at you. Obviously the way it was phrased, the answer was no. But why? Well, if you scale and add two functions, it's not necessarily going to give you a brand new one. So for a fun example, at face value, these look like completely different functions. Sine of 2x and sine of x times cosine of x. But they're not. Remember, 2 times sine of 2x is 2 times sine of x times cosine of x. So even though these look like very different functions, and they are different functions, an identity reveals to us that, well, scaling and adding them isn't going to make anything new, right? If I were to scale and add these together, I'm just going to get a scalar multiple of y2. So I didn't really create a new solution, I just, right, by superposition, I already knew y sub 2 times this scalar combination was going to be a solution. So scaling and adding them together didn't actually make any new solutions. So this leads us then to a definition that we have to make, right? So that idea, find two solutions, scale them together, and add them up, and that gives me the general solution, will work as long as the two solutions I have satisfy something. All right, in this example, it gives us a pretty good idea of what I need. So we're going to say that functions, any number of functions, are linearly independent if given constants, so that the linear combination of them, so take them, add them up, and scale them, if that equals 0, the only way that could have happened is if all the scalars are 0. So in other words, the only way a trivial linear combination, so a linear combination that gives me the 0 function, the only way that could have possibly have happened is if all of the scalars were 0. So in other words, I couldn't choose scalars so that things scale up and add together and get me to 0. So in other words, my functions are not linearly dependent upon each other. So I can't scale and add them and get back the same stuff. Right, so linear independence here, this is precisely getting at what we want. We want to be able to scale and add and create something unique with that. Right. Whereas linear dependent is what happens if you're not linearly independent, which means we can find constants, not necessarily all equal to 0, that do give me the trivial linear combination. Okay, so right, it's worth noting this is very precise and very technical, but it's capturing a very clear idea. I want to be able to scale and add things together and have that create something new. Right, I don't want to be in the situation where scaling and adding doesn't give me anything new. It just gives me back what I already know, and that's what linear dependence is capturing. Right, so this is a classic example of mathematics being the poetry of logical ideas. Right. That's an Einstein quote. That's what Einstein legit said. That's what math is like in his obituary for Emmy Noether. Check out Emmy Noether, by the way, if you've never heard of her before. Pretty amazing mathematician. But anyway, so Einstein in her obituary points out that the work she was doing was the poetry of logical ideas, and really what that's getting at is. Right, what is poetry? Poetry is, I had a feeling, and then I'm gonna pick very precise language so that when you read the words that I wrote, I'm going to elicit the same feeling out of you. So poetry of logical ideas, then, is I'm going to capture these logical thoughts, right? I want to be able to scale and add things together and make sure that creates something new. And I have precise language describing exactly that logical feeling. Okay, so cool. This is tight, right? This is some tight stuff right here. Right. Now, this is nice and all, but let's actually get a taste for it. Let's see how this works. So, let's look at e to the x and e to the minus x. So, we saw those appear as solutions for the differential equation y double prime minus y equaling 0. Okay, well, are these linearly independent? All right, we'll scale them up, add them together, and set it equal to 0. If I can find non-zero scalars that work, then they're dependent. But if the only way this holds is if they are both 0, the scalars C1 and C2, then they're independent. Alright, so what should my idea be? Well, let's plug in some numbers, right? I'm supposing this is true, and x is an independent variable, so just plug in some stuff. Alright, so 1 and 2 seems pretty good. Now, if we look at the two equations we get, c1e plus c2e to the negative 1 equaling 0, and c1e squared plus c2e to the negative 2 equaling 0, I probably want to multiply that first equation maybe by e. Right, that gives me 1e squared plus c2 is 0, which would coincide with this equation right here. And hey, look at that. C1e squared and C1e squared, I've matched those terms, so I can now solve for C2. And that forces 1 minus e to the negative 2 times C2 equaling 0, which means that C2 itself must be 0. Nice. So now, note what I did here. I literally just began with this equation. I plugged numbers in, and then I just did some experimenting. There was no procedure here in my mind. I just knew something and I plugged in some stuff. I've got, of course, some prior experience that I'm bringing to the table. But in reality, right, all I did was plug numbers in and go, all right, I got to get stuff to match up here. What can I do? Well, and then I noticed that, well, I can make this look like that by multiplying by e. Okay. All right, and that isolates C2 then, and I got C2 was 0, so we're halfway there to verifying linear independence. All right, plug that back into any of the equations we've already established. So I plugged it back into this one. And e is definitely not equal to 0, just like 1 is not equal to 1 over e squared. So that means that c1 is 0. So these two functions must be linearly independent. If I scale them up and add them together and get 0, the only way that was possible was if the scalars themselves were 0. So in other words, scaling and adding e to the x and e to the negative x together will always produce a new function. It's never going to give me redundant information unless I used trivial scalars. Right, that's the idea. That's what we want. We want to be able to scale two functions together, scale two functions and add them together to create a new solution. Right, because that's how we are going to get the general solution to second order linear homogeneous differential equations. Right, now let's get an example of something that's dependent, and we already knew this. Sine of 2x and sine of x cosine of x are linearly dependent. I can find scalars that are non-zero that add up and give me 0. So I can make the trivial linear combination using non-trivial linear using non-trivial scalars. Okay, cool. Right, so here we see that the amount of work you had to put in to verify independence is significantly less than the amount of work they have to put in to verify dependence. Dependence is just find the things that work. Independence is show that the only things that could work are zeros. That's a lot more work that has to go into that. Right, so that being said, going directly from the definition is going to be a little bit difficult, depending on the situation. There's a better way. Okay. So, given functions y1 and y2, the Wronskian, named after a mathematician named Wronski, who is now going to join up with the Tampa Bay Buccaneers. I'm dating this video, I guess, but I'm very excited for this upcoming season. Let me tell you, it's going to be silly. All right. Anyway, so here's how we define the Wronskian. So if this notation looks very familiar, then you've had some experience with linear algebra. Now, if you haven't, don't sweat it too much. We will actually talk about this in a lot more detail later on, but basically, the Wronskian is defined to be the following quantity. It kind of looks like the product rule, but there's a minus sign. And if you've ever heard of a determinant, then you see exactly what's going on here. Alright. Phone randomly went off. I wonder if the thing caught that sound. I try to be isolated from everything, but, can't guarantee anything. I'm surprised my daughter hasn't broken in on one of these recording sessions yet. And, alright, let's keep going. I'm blah, blah, blah. Okay, so, we've defined the Wronskian here. And again, if you've had some experience with linear algebra, this looks very familiar. Alright, now, if we have that our functions, y1 and y2, are linearly dependent, that means I can scale and add them together. And the scalars can be chosen to be non-trivial, so we can assume, without loss of generality, that C1 itself is non-zero. So, subtract that term over. Taking the derivative of the original, well, derivative of 0 is 0, and derivative is scaling, so that's fine. And now, here's the slick trick. Multiply this thing by negative y2, okay? Negative C2y2, that's what I was looking for. C2y2 is equal to negative C1y1, so this quantity right here turns into that. And now we could factor C1 out of the whole thing, and we get C1 times y1 y2 prime minus y1 prime y2. And that means that the Wronskian must actually equal 0, right? C1 is a non-zero constant, so that means this quantity right here must be 0. So what we've now demonstrated, right, nice little explanation here, if you are linearly dependent, then your Wronskian must equal 0. Okay, so let's rephrase that. Let's reiterate that. If you are linearly dependent, then the Wronskian must equal 0. So, if I take my functions, take their Wronskian, and I get something other than 0, then we know that we cannot be dependent, because dependent means that the Wronskian is 0. So, if the Wronskian is non-zero, that means we had to have been independent. Ah, there we go. Beautiful. So now we've got a very slick and easy way of detecting linear independence without having to go through the whole rigmarole that I did before. Right? All I need to do now is compute the Wronskian. If my Wronskian is non-zero, then I'm linearly independent, and I get to wash my hands and be done. Now, if my Wronskian comes back as 0, I gotta be a little careful. It turns out that, for the most part, the answer is that if the Wronskian is 0, that means you're dependent. But note how this is phrased. This is, if dependent, then Wronskian is 0. So if it is raining, then the grass is wet. Now, if we know the grass is wet, it doesn't necessarily mean that it's raining. Right, A implies B is not the same thing as B implies A. But it turns out that for most cases, the Wronskian being 0 is equivalent to dependence. Your textbook goes through there's some very technical garbage about it, and we don't need it. But if you're interested, check it out. It's a very if you go to the Wikipedia page for the Wronskian, there's like a whole section devoted on to the very common mistake is Wronskian equaling 0 is equivalent to dependence. It's equivalent under some other assumptions, but everybody forgets them. But anyway, check it out if you're interested. But for our purposes, let's give it a go. Here's two functions, x and e to the negative x. I want to detect if they're independent or dependent. The Wronskian now gives me a quick way of getting to it. Right, rather than setting up the whole scalar thing and adding them up and plugging in values and blah, 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 I can just go ahead and compute the Wronskian. I immediately see my Wronskian is non-zero. So boom, it's a linear independent. Much easier. A hell of a lot easier. That's what we're always going to do from this point forward. We are never going to do that scalar thing again, right? That is the definition, right? It's capturing what we were talking about. I want to scale things up and add them and create something new, right? But now this test using derivatives, just boom, it immediately tells us that we're good. Okay. Right, so as I said, if you get something non-zero, that it guarantees independence. If you do get it's equal to 0, okay, then you gotta do a little bit of work. That gives some evidence that it actually might be dependent, so need to make one step further then. You got to do a little more investigating. But for our purposes, non-zero, we're happy and we're good. All right, excellent. Okay. So, here's the big fact now. For any second-order linear homogeneous DE, again, looks like this, the general solution will be a linear combination, C1 times Y1 plus C2 times Y2, where Y1 and Y2, not only are they solutions to the differential equations, but they have a non-zero Wronskian. They are linearly independent. Such a configuration is going to be called a fundamental set of solutions to the differential equation. So, if we're trying to solve second-order linear homogeneous differential equations, we need to do two things. First, find solutions, y1 and y2, and then second, verify that they're linearly independent. So if you find solutions, check their Wronskian, it's non-zero, then boom, you've got a fundamental set of solutions. So as we've already seen, e to the negative x and e to the x and e to the negative x, those are solutions to the differential equation y double prime minus y equals 0. Furthermore, they have to be a fundamental set of solutions because those functions, as we know, are linearly independent. Jumping ahead here. Right, so that means the general solution now will be c1 e to the x plus c2 e to the negative x. Okay. All right, so now, there we go. We now know what solutions to a second-order linear homogeneous differential equation are going to look like. They're going to be a linear combination of linearly independent solutions. Okay, so in order to solve such things, we need to find two solutions, y1 and y2, and we need to check that they're linearly independent. So let's do that. So here is an example. Good time to pause the video and give it a go yourself. Okay, so you want to verify fundamental set of solutions, so that means we need to verify their solutions and verify they're linearly independent, so that when I scale and add them together, I create a true new solution. Okay. Right, and two derivatives, two unknown scalars, makes sense. Okay, so let's give it a go. Okay, so the first thing is we want to verify that y1 and y2 are actually solutions, so just plug them in. Put them into the DE and make sure they work. And they do. Okay. Now that we know that, we want to now check the Wronskian. Right, and this is the more interesting part. All right, we set up the Wronskian, and we see that it's 7 e to the x. That's non-zero, so they must be linearly independent. So I have two functions that are solutions to the DE. They are linearly independent. Very happy about that. So that means they are a fundamental set of solutions, and thus the general solution of the differential equation is a linear combination of e to the negative 3x and e to the 4x. Okay, beautiful. Yeah. So, that now gives us exactly the flavor of the next couple of weeks here. Right, solving second-order linear homogeneous DEs, we just got to find two solutions, and then verify they're linearly independent. And that's it. Beautiful. Okay. So that's pretty much the story, right? All right, well, we're not quite done. Right, we now have the answer for the homogeneous case, which is solutions are going to be a linear combination of two linearly independent functions. What about the right-hand side not equaling 0, though? The non-homogeneous case. Okay. All right. So what are solutions to this going to look like? All right, well, let's say we had two solutions, u and v. Scale them up, add them together, multiply them by, where you're scaling by the functions a2, a1, a0. You should get this. Let me take the difference of the two. Subtract these two equations. The right-hand side, right, do the thing you want to do. Cancel those. You get a 0 on the right-hand side. Hey, look at this. If I have two solutions to the non-homogeneous, their difference is a solution to the homogeneous. So that's why we looked at the homogeneous first, because the non-homogeneous is secretly the homogeneous case in disguise, right? That's the slick move that we pull off a lot in mathematics. So look at one case that really captures everything. All right, so that means that u minus v has to be a linear combination of a fundamental set of solutions to what we're going to call the associated homogeneous equation. So if you're studying a second order linear DE, it always looks like this. The first thing you're always going to want to do is attack its homogeneous version, the associated homogeneous, because any two things that are solutions here, their difference is going to be a solution to the homogeneous case. All right, so that means, the big punchline here, any second order linear DE, the general solution will be a summation of two things. Y sub h, which is the general solution to the homogeneous equation, and y sub p, which is any solution you can find to the original differential equation. So to solve any second order linear DE, two things must be done. First, find the general solution to the homogeneous equation, which amounts to finding two linearly independent solutions, y1 and y2. Then go back to the original one and find anything that works. That plus the homogeneous will give me the general solution. Okay. So because of that, y sub p is usually referred to as a particular solution, one that we've particularly found. Okay. All right, so that answers our question from the beginning. What are solutions going to look like? We are going to go hunt second order linear differential equations. Well, now we know what answers are going to look like. We know exactly the form they're going to take. Okay, nice. So let's wrap things up today with another example. We are going to figure out what the general solution of y double prime plus y equaling x cubed. Here's a second order linear differential equation. We're going to get its general solution. Yeah. So we just talked about how you should do this, so you can take a moment of pause and work out on your own, and then come back. So I'm going to take a sip of my coffee. Okay. Okay, so first things first, we got to solve the associated homogeneous, which means ignore the x cubed for the moment and look at y double prime plus y. Okay. Find me a function whose derivative plus itself gives me 0. Well, that means I need a function whose second derivative is negative itself, and hopefully immediately sine and cosine jump to mind. Right. If they didn't, that's okay, don't worry. We'll talk about a more robust way of solving these later, but for now we're just doing some general investigation. Now, the Wronskian is equal to 1, so hey, those are linearly independent, and thus they form a fundamental set of solutions. So that means the general solution to the homogeneous equation, y double prime plus y equaling 0, is c1 cosine plus c2 sine. This is a good equation to burn into your mind. Y double prime plus y equals 0. The answer is c1 cosine plus c2 sine. So go to your math box, open it up, and see where you got the quadratic equation. Put this right next to it. Right, or maybe where you got all your trig identities in your math box. Go put that in there. Close up your container. Put it under the shelf or wherever you got all this math knowledge in your mind palace. Okay, there we go. All right, so we've solved the associated homogeneous. So now we need to find a particular solution. Once we find that, we have solved it. Okay, so how am I going to attack this? Right. At first glance, you might look at this and go, I have no idea, dude. What are you expecting out of me? All right, well, we will talk a lot more about how you solve such equations, how you find particular solutions. There are techniques. But one thing you could do is just guess, right? I have a function whose derivatives added to itself is a polynomial. Pretty good guess would be a polynomial, and if you just want to try something, well, the right-hand side's x cubed. Does that work? Obviously it doesn't, but it does give me an idea, right? When I plug in x cubed, I almost get the right thing. I just got this pesky 6x right here. So let's try x cubed minus 6x. Well, the second derivative will still be 6x, right? The derivative of x cubed is 3x squared. Its second derivative is 6x. The second derivative of negative 6x is 0. So the terms knock out and, haha, nailed it. So the general solution to this is C1 cosine plus C2 sine plus x cubed minus 6x. Nice. Okay, so I stumbled onto the solution, right? And note that all I had to do to find the general solution was solve the homogeneous, which amounted to finding two solutions and then just verifying that they were linearly independent. Again, all you have to do, just find two solutions. I don't care how you find them, just find them. Scale them up and add them together, that gives you the homogeneous solution. Then particular solution. Again, just find it. I don't care how, find it. That's exactly what I did. All right, nice. So there we go, setting up the table for the dinner. That will be chapter 4. Okay. Okay, so now we know the story. Second order linear DEs. They can always be solved. And if I want to solve them, I've got two things to do. Solve the homogeneous, find a particular solution, add those up, and I'm done. And that is literally it. That is all you have to do. I am not joking. That's all we have to do. Okay. How hard can that be?